We present Neural Experts, a novel mixture of experts architecture for implicit neural representations. Implicit neural representations encode signals using some neural network architecture, often modeled as an MLP. More formally, given an input coordinate, our goal is to predict the signal's value at that point. This formulation can apply to many different signals. For example, representing images, where the input is the pixel coordinates and the output is the color of that pixel. Or representing surfaces, where the input is the XYZ point coordinates and the output is the signed distance function of that point to a surface, making the zero level set of that function the desired reconstructed surface. MLPs have two inherent drawbacks. The first relates to parallelization and scale. MLPs process each coordinate by the entire network. Therefore, all parameters have to contribute to the output of every point in the domain, making parameter optimization difficult. And the second is a locality limitation. A desired property of INRs is for features to change rapidly to allow modeling of sharp boundaries, which does not arise naturally in optimized MLPs due to spectral bias. This begs the question, are MLPs the best choice for implicit neural representations? In this work, we propose a novel mixture of experts architecture for implicit neural representations that simultaneously subdivides the domain, reconstructs the signal, and enables parallelization. A vanilla mixture of expert INR architecture, similar in principle to the one proposed by Jacobs et al. For classification, is composed of two modules, a manager model and an expert module. Both modules get the input simultaneously. The experts module consists of multiple experts, and each expert provides a prediction for the input data point. The manager, on the other hand, essentially selects the best prediction out of all expert predictions by using an argmax operator over a score vector. Our experiments showed that this vanilla formulation for INRs is not able to adequately reconstruct the signals. Therefore, we proposed the neural experts architecture. It is also composed of MLP-based expert and manager modules. In our architecture, the expert module first feeds the input coordinate into an encoder module that is shared for all experts. The expert encoding is then fed into each individual expert to get each expert prediction. The manager module separately encodes the input coordinate and then concatenates the manager's encoding with the expert encoding before feeding both encodings to the final manager's MLP to get the expert selection vector. Intuitively, the manager learns to subdivide the space, and each expert is in charge of reconstructing the signal in each subspace. This is trained using a mixture of experts loss that scales the reconstruction loss of each expert by the manager's confidence of that expert being selected. This formulation allows us to inject different biases into the manager's subdivision by imposing predetermined expert assignments at initialization using a pre-trained manager. In this example, we show the initial manager's assignment for different assignment types. Here we can see the manager's assignment after the full training procedure. It can be seen that in most cases, the manager is able to move away from its initialization and learn to cluster region based on the input signal. The quantitative results show that random initialization pre-training performs the best out of all initialization options, which is particularly useful as it is signal independent. We evaluate the performance of neural expert on different reconstruction tasks, including 3D surface reconstruction, where we can see a significant boost in performance attributed to the manager's subdivision. We also report results on image reconstruction. Here, we also highlight that our architecture is independent of the activation, and we show improved results on multiple activation functions, including soft plus, sign, and finer. For more qualitative and quantitative results, please refer to the paper. In summary, in this work, we introduce a mixture of expert architecture for implicit neural representations, which simultaneously subdivides the domain, reconstructs signals, and enables parallelization. Additionally, we derive a novel manager architecture and initialization that enables domain subdivision without ground truth. Thank you for listening. The code is publicly available. Please check out our paper and project page for further details.